Start the recording. Right, so where we left yesterday was discussing, we showed that the Fourier series, we started off by recalling that the Fourier series applied to periodic signals. And if the signal was not periodic, then what the Fourier series evolved to was something called the Fourier transform. And we derived it from the Fourier series by saying that let's make the period get bigger and bigger and bigger until it gets so large that all you really have is one cycle of whatever the signal is. And we use that to derive the Fourier transform. And the version that we settled on was the one that is on the screen here, because it looks very close to the Laplace transform in appearance, especially what we call the forward transform, which is the one that takes you, remember this is taking you from the time domain to the frequency domain. So going from time to frequency, the forward transform, so you take xt, and what you get when you transform it is a function of j omega, a function of frequency. Some books put it like x omega too, so you will see that appear. But the j omega is just more correct because of the fact that the sort of argument of the e is really a minus j omega and not just plain omega. And then, of course, if the transform has to be a valid mathematical transform, you have to have a way of going from frequency back to time. And this is where the inverse transform comes in. And pretty much the same sort of format again as the Laplace transform. The inverse transform takes the frequency domain result, and then you multiply it by e to the plus j omega t this time, and you integrate, and you come back into the time domain. All right. In this case, if you have complex numbers, then of course you have the complex integration. In the case of the Laplace transform, it's a little bit more complex. So we generally don't do that normally as a routine. We tend to use lookup tables and the like. So we were comparing now, so between the Laplace and the Fourier transforms, the similarities means there are less things for us to remember. The differences are the ones that we're going to have to focus upon, right? So it's kind of like learning Spanish and Portuguese. There will be very similar verbs and words, but there will be a couple of things that will be totally different or spelled differently. The main difference here, obviously, looking at it, first off, are the limits of integration. The Laplace transform, the version that we use because we're dealing with, and these things keep coming up, we try to deal mostly with causal signals, and wherever possible, our Laplace transform integrates from basically 0 to infinity. As we said in our own use, that we integrate a little small, a minuscule time before 0, so that if the signal changes at 0, for instance, a unit step, that we catch it in the integration. So we're not integrating at the same time the signal is changing. The Fourier transform, because it's derived from the complex Fourier series, has to run from minus infinity to infinity, right? So that's the one major difference here. So naturally, because of those two limits, some of the transform results will look the identical, where it's just a simple matter of, if you were to replace s with j omega, you can take the Fourier transform, you could almost derive the Fourier transform from the Laplace result. But there are other transforms that it doesn't work quite that way, because of the fact that there's a lower limit of minus infinity on the Fourier transform itself. Okay, so some of the properties, of course, is that the Fourier transform is linear, like the Laplace transform, which helps us a great deal in that if something is complicated, we can take the individual transforms and add them up and scale them, with gains or attenuations, as the case may be. right? So that first property, and that saves us a lot of work. Remember, for the most part, in our applications and in most of your engineering work, you will be dealing with linear time invariant systems, right? Occasionally, you'll get some nonlinear stuff, and you will see that in the specialized cases when they do come up. Right, other properties, the Laplace transform on the left, the Fourier on the right. Time scaling, you remember we did some of that mechanically. So if you take a signal and you scale it by some factor A, right? And we saw that if, depending on if A was a positive integer greater than 1, or if it was a fractional integer, then you would have either expansion or compression. In the case of the Laplace transform, if A, whatever A was, the transform was 1 over A x, and wherever you had S, you scaled S by A. In the frequency domain, the same thing happens, is 1 over A, and you scale the j omega component by A. Time shifting, the one below, so you shift the signal, and we know what this is, that the signal, instead of whatever is a t0 position, has shifted. It is a delay, so you delay it, and you multiply it by the Laplace transform. It's the same thing, but it's going to be multiplied by e to the s minus st0, whatever that is. T0 is normally a number of some sort. In the case of the Fourier transform, it's e to the minus j omega t0. So it's identical if you were to take the s and replace it by j omega up to this point. Then on top there we have the frequency translation. We're going to talk about this in a little bit of detail if we get to it today, if not at the next class. This now is the principle of operation this is why communication systems work. This actually is a core of modulation, L-A-T-I-O-N, right? That mathematically explains modulation, and we'll talk either if we get there today or if not, next class. This one, you didn't realize it at the time, but it's the same thing applying in the S domain or with the Laplace transform. Okay, here is the first time a bit of a difference comes in. In time differentiation, the Laplace transform, if you take a dx dt, you have sxs, and you have this thing because we are starting at x naught minus, so there is an initial condition. In the case of the Fourier series, sorry, the Fourier transform, we are going from minus infinity to infinity. So there's no such thing as an initial condition. Okay? So in other words, the Fourier transform will apply to situations, for instance, if you are dealing with a non-causal situation where the device, for instance, or the signal has been on and the analysis is taking place when you're jumping into the middle of how everything is working, right? That's conceptually how it works. But basically what it means is that the Fourier transform of a derivative, like the Laplace transform, is j omega x of j omega, but there's nothing else, no initial condition to take place. Now, this again is a good reason why we write it x j omega, because there's a j omega in front, right? If you get into the habit of writing x omega, as we do sometimes for shorthand, or you're writing up, or you're typing it up and so on, there may be a tendency to put omega in front here, which is, of course, wrong. Okay? So just remember that. So the first major difference, of course, is that the Fourier transform doesn't address or doesn't handle initial conditions, because it is assuming that everything has been going on from t equal minus infinity to infinity, or for more practical terms, that the thing has been on and the signals have been existing for a very long time. Right? If there are any questions, of course, feel free to ask or type it up in the chat, and hopefully I'll be able to see it. So here's this now, and this will tie back to something else that we said long ago or early on. What is the Fourier transform of the impulse? Well, again, every time you evaluating anything with an impulse, you have to remember the thing called the shifting property of the impulse. So the Fourier transform xt e to the minus j omega t dt, and you're integrating. So xt is delta t. Of course, the impulse function sifts out, right? Remember, it sifts out anything at the point of the impulse. So delta t is an impulse at t equal to 0. So this is going to sift out the value of e to the minus j omega t at t equal to 0. Okay? And e to the power, any e to the power 0 is 1. So the signal is an impulse. The Fourier transform, right? The Fourier transform x j omega is equal to 1. So what does that look like? If I were to plot 1 against frequency, that is a constant horizontal line of amplitude 1 going from omega equal minus infinity to omega equal to infinity. Right? Now, this is one of the reasons, you remember early on when we said that there were certain signals that when if you were able to create that signal and use it in testing or even mathematically, that the signals tested the system to the extreme. And one of them that we saw was, of course, the unit impulse. And this is why I mentioned that we'll meet it further when if you recall, when we do the Fourier transform. So this is what happens. When you put an impulse into a system or something fairly close, and we'll talk about that in the little example coming up to, if you get something fairly close to an impulse, when you put that into a system, what you are doing is the equivalent of injecting a varying frequency that is going from 0 hertz to incredibly high frequencies. So you're subjecting the signal, the system, or whatever you're testing. It's like you're sitting down with a signal generator on the input of the system, and you start at low frequencies, and you send all the frequency in as high as the signal generator can go and beyond. So the system is subjected just by the ability, the frequency content of an impulse. You, by doing an impulse test on a system, you actually are able to subject the system to an incredibly high frequency input. That is why it's such a critical test, and why we do it even when you get the transfer function. The transfer function now tells you what sort of frequencies the system is going to respond to in response to an impulse being put in. Fair enough? Yeah, maybe? Right? So, good. So let's see now, we know a practical impulse is kind of hard to make. So let's see what happens if we go back to something looking like this. Here's a pulse. The pulse is width A and height 1 over A. Right? So that the area of the pulse, the area under the pulse is equal to 1. All right? So what is the Fourier transform of that? So you sit down and you know go to the equation, and the equation for the Fourier transform will be minus infinity to infinity, right? X t e to the minus j omega t dt, right? And of course, in our case, this limit now is going to be minus a over 2. Here is going to be a over 2. And what is xt? Between those limits, xt is 1 over a, right? Right, so 1 over a. If you do that and you manipulate a little bit, you're going to get an integral in terms of e to the minus j omega t and e to the j omega t. And then you use the sine, the Euler's relationship between sine and e and so on, and a little bit of manipulation, you're going to land up with something looking like this. Sine omega a over 2 over omega a over 2. And we call this function, there's a general term for it, a sinc. Actually pronounce it like that, sinc, S-I-N-C, a sinc function. You're going to meet that as well in communications quite a bit. So that the Fourier transform of the pulse, we call the pulse PT, so P of j omega is a sinc function or of sine x over x. That's what a definition of a sinc function is. If you look at it in MATLAB, it actually exists as the keyword sinc, right? So sine x over x. So anytime you get something looking like in this relationship, sine x over x, it is sinc x. X, of course, is omega a over 2. Now, what does that look like if you plug it? If you plot it, sorry. If you plot it, of course, you have to remember that you're plotting in radians, right? So you're calculating the value of sine omega a over 2 in radians. If you plot it, you get a function that looks like this, right? This is the magnitude of the function. The actual sinc function looks like this, right? So it has this, it goes, and it goes on for quite a while. It goes on in theory for a long time. So the magnitude of it is what we're showing here in blue, right? So this is the magnitude of the function, okay? So let me just clear that mess a little bit. Right, so this is sinc omega a over 2. And of course, you have to remember that sine x over x, as we did yesterday, as omega a over 2, as this value, as omega gets close to 0, sine of a radian value close to 0 is omega a over 2 over, of course, omega a over 2, which is 1. So the sinc function peaks at 1, right? So now what is this telling us now? You look at this thing, and I have, I started off, remember, this is the Fourier transform of something that looks like this in time, right? Minus a over 2, and the height is 1 over a. So this is a pulse, right? So what happens now? What happens now if a starts to get small? If a gets to small, if a starts to get small, what happens to the limits a over 2 and minus a over 2? They get closer to 0, right? So what's going to happen here now, as a gets smaller, you're going to have this thing, you get smaller, you're going to have here come in, so a over 2 is going to come in here, and 1 over a, exactly, Stephen, 1 over a gets smaller, so 1 over a starts to get bigger. So as a gets smaller, this pulse does that. And if you keep going smaller and smaller, right? So if I can make a small, 1 over a starts to get large, but then what happens in the frequency domain? This point, these points here are functions of omega a over 2. These are where omega a over 2 becomes 0. So if a starts to get smaller, let's go back to the function here. So as omega a, so as a gets smaller, this bit below here starts to get bigger, right? So in other words, these points here start to move further and further away. So as A gets smaller, this starts to look like that. And if you keep getting A smaller and smaller, it spreads and then flattens and flattens. Eventually, the limit, of course, is when A is 0, so that you have a 0 width and an infinite height, which is a unit impulse. So you can actually, of course, you can't get that, but what we are seeing is that if I could make electronically or however, if I can make a pulse that is fairly narrow and fairly tall, once I retain the area as 1, I can get a function whose frequency response is very, very flat over a long range of frequencies. In other words, I'm getting closer and closer to what the real spectrum of the impulse is. We can practically get this to go something like that, where this is in the high megahertz range. Yeah, exactly. So the limit as A goes to 0 is an ideal impulse. Exactly. So, right. So now, well, we know how to create pulses. We already saw in our what do you call it, electronics class, that it's possible to create a monostable that can give you a pulse, right? So you can create the pulse electronically by using a timer circuit of some sort, an op-amp with a timer, and you choose the capacitors and resistances to give you a very narrow pulse. It will saturate, you control the pulse in relation to whatever the saturation voltage of the op-amp is. Of course, you use a very, very fast op-amp too, so they can get the sort of sudden change that you want. So that electronically you could create, it is possible to create a very, very narrow, very tall pulse. And that now has a very wide frequency response because of the Fourier transform behavior of the pulse. And practically now, that is what they do when manufacturers test loudspeakers. One of the things that they do when you're making a loudspeaker, like a speaker box for entertainment purposes and so on, is that you remember the audio frequencies humans hear from 20 to 20 kilohertz, more or less. All right. But what you need is when you make a loudspeaker, you want it to over that audio frequency range. If you measure the audio frequency for the loudspeaker, you want it from, let's say this is 20 hertz and this is 20 kilohertz. You want it as flat as possible over as long, as wide a bandwidth as possible, right? The better the speakers, the lower the frequency, and over the human audio range, you try to get it to remain as flat as possible. So what they normally do is that you take the speaker box and they would take you're manufacturing it, so they will take a typical unit and they will put it into a special room that doesn't have any echoes. They call it an anechoic chamber. And inside of there now, they would send, I mean, the traditional way you would do it would have been to hook up the speaker to an amplifier and hook a signal generator to the amplifier. So you start with low frequency, so you put in a signal at 10 hertz, and you have a microphone measuring the output of the speaker. You put 20 hertz, you measure the output, and so you go for the entire range up until you pass 20 kilohertz, and then you plot out the response and see what you get. Now, because of things like what we just saw, it is possible using computers, and in fact not possible, that's how they do it. Instead of sitting down with a manual approach, what you do is to generate a series of pulses. And because because of this relationship that we just derived here, I can make, if I know what A is, then I can plot P or J omega very easily. So if I know what P or J omega is, and I send that into the loudspeaker, then I could derive, because it's all being done now automatically, I know what frequencies I send in, and therefore when I put the pulse in, the microphone will pick up the pulse that the loudspeaker sends out, and I compare the two of them, and I could actually plot the frequency response of the loudspeaker that way. And that way they can do it. And in fact, because the pulse is so short, you don't have to do it in an anechoic room, right? You just do it out in a place where you don't have echoes and reflections coming back. So they put it in there, and they send the pulse, and they do the measurement that way. So it's a very interesting application of this. And then communication, people use this type of application all the time. Every time you hook up, for instance, an optical fiber cable, like in UE, for instance, the buildings are linked by an underground fiber optic cable that carries the high-speed network information around the campus. When you hook up that, one way to check to see if the cable is working is to send a pulse down the cable. So again, a pulse has a known frequency signature. If the cable is working good, then at the other end of the pulse, somewhere down the road, 1.5 miles down the road, a piece of equipment will pick up the transmitted pulse, and it will compare the frequency, the spectrum of the pulse to what was known to be sent in. And if there's too much of a deviation, we know that there's something wrong with the cable. Okay, so very practical applications of in real world of the Fourier transform, and you're using it without even thinking why. I mean, the people who came up with it would have been engineers, and they know exactly what they're dealing with. Okay, so questions? I want you to try this derivation and make sure you get it. Okay, it will appear in a problem set somewhere too, but do the derivation here. Right, do it, run the integration, and make sure you get it. Yeah. Right, so let's just dig around a little bit with some other matters here. Right, so this now, again, just to sort of summarize, graphically now, this is what we've been saying, that the Fourier transform takes the spectrum of a non-periodic signal, and we understand that the sort of derivation assume that the period is so huge that we just left with one sort of pulse of the signal, if you like, and it gives you a spectrum. So this diagram is just showing an arbitrary signal on the left-hand side and what the signal spectrum is on the right-hand side. And notice that x at j omega runs from minus omega s to omega s. Okay, we do that because not because of the fact that they are negative frequencies, but because this is a complex integral or complex calculation, so that the answers have to be appearing as complex conjugates. So this signal now has a bandwidth of 2 omega s, right? It's running from minus omega s to omega s, right? Just a graphical derivation. And this property that we said, so the frequency translation property was saying that we just discussed, if you take xt and you multiply it by e to the j omega naught t, what happened is that the spectrum of the signal, if this was the original spectrum here, and the spectrum is running from minus omega s to plus omega s, this now, remember, this is just like our time delays and so on. This is a frequency delay, if you like, or frequency translation. Let's not say a delay. So what is this? X of omega, if I told you t, x at t minus 3, it now means x of t has now shifted up to the point where t equal to 3. So the frequency translation is the same thing, that x omega has now been shifted, and the term they use, of course, is translated, so that it is now centered on omega 0. So that the original bandwidth of the signal is still the same. We didn't change anything. It still has a 2 on omega, on minus omega s plus omega s, but it's now centered on omega 0. Yeah, that is what you understand. What the result of that operation is graphically. What we're trying to say. Yes, no, maybe. Yeah, makes sense. Right, exactly right. So what are you doing? We are shifting so that the spectrum, the spectrum is centered around omega 0, the DC value originally. If I multiply the signal in time by e to the j omega 0t, then the spectrum is now shifted so that it is now centered upon omega 0. And this, I was saying, perhaps, yeah, but then, yeah, more mathematically correct, I suppose. I could put x j omega minus j omega 0, right? But we understand what we're saying with, and we're dealing with the magnitude of the spectrum here. So we could get rid of the j sign once we're dealing with the magnitude. Now, this is why we are able to communicate now, why you're able to listen to a radio station on your car, and why you're able to talk over your cell phones. This is the principle of modulation. What modulation does, you remember, if, well, I don't know if you're doing any communications as yet, but remember what modulation does. It takes the normal, for instance, our audio signal. You can't, the frequency is too low to transmit any sort of distance electronically. So what you do is that you multiply the audio signal, or you combine the audio signal with something called a carrier. The carrier is a very high frequency signal, electromagnetic signal, that you can now hook onto an antenna and send the energy down the road. So this is exactly what's happening. E to the j omega naught t. And you remember, in real terms, this is cosine omega naught t plus j sine omega naught t, right? So you have a cosine signal here. Forget the sine for the time being, right? That is handled in it. But e to the j omega t is really a complex sinusoid. So if omega naught was, let's say, a 95 megahertz signal, what is going to happen if I multiply my audio signal here with a 95 megahertz signal here, the normal 20 to 20 kilohertz audio signal here is now shifted and centered on 95 megahertz. And you're now able to put that into send it to an antenna with some electronics and transmit it down the road for somebody else to pick up. And what they do in communication is that you tune to the carrier frequency, which is the omega naught inside of here, and you pick up the entire signal, you remove the carrier, and you get left with your original signal coming back. You're going to talk a lot about that when you do your communication course or courses with Dr. Adams and Dr. Malaliu, and this whole thing about modulation is going to crop up. But in terms of the mathematics behind it, and when they talk about modulation and they start to talk about the spectrum being translated and centered on the carrier frequency and so on, now you know why, right? It's because of this particular property of the Fourier transform. Yeah? Fair enough? Yeah, fair. Okay, I'll take fair. So we did the spectrum of the impulse, and we saw that the unit impulse had a flat spectrum, an infinitely wide spectrum. We did the spectrum of a pulse, and we saw that if we made the pulse narrow and tall, that the spectrum moved from the sinc type function spectrum to a flatter and flatter spectrum. And if in theory we can make a pulse very, very narrow and very, very tall, we can almost get the flat spectrum of the ideal impulse. So let's look at the other signal that we tend to use a lot, which is this unit step. So what would be the Fourier transform of this? Well, of course, the first instinct, of course, is to plug that into our expression for finding the Fourier transform. Either the j omega t, and you integrating between between minus infinity and infinity. But then you're going to run into a problem, because as soon as you plug that in, you remember the function in unit step is 1. So if run that in there and you start to find the limits now, you start to run into these things. What is the limit of cosine omega t, for argument's sake, and sine omega t as t approaches infinity? Sine and cosine oscillate between plus and minus 1. So at that point, this technically we need another approach to solve this. Right? You can't just simply do the integration because it's not going to work for you. So we look at that now, and then we say, okay, we remember that there's a similarity with the Laplace transform, and we saw that if we replace S with j omega, that under certain conditions, the Laplace transform, by replacing S equal to j omega, you get the Fourier transform of the signal or the transfer function you were dealing with. Now, the one other part you have to remember now is that a difference with the Fourier transform and the Laplace transform has to do with that thing with the Fourier transform deals with a frequency domain. So we are partially correct. Part of the answer is 1 over j omega. So you're all right there. But we need to account for another bit of the answer here. If you look at the unit step has a DC value. You remember when we were doing when we looked at the Fourier series and we had these pulses yesterday, we saw that there's an average value, and that the average value depended on the duty cycle. Right? The wider the duty cycle, the higher the DC value was. The smaller, of course, it dropped. So here we have now, if I were to take one of these pulses and stretch it out, so that all I have left is this. Just basically is my unit step here. It's a very large, and it will come back down at time equal to infinity. Because it's on and off for half the time, it's off for minus infinity to 0, and it's on at value 1 from 0 to infinity. Instinctively, you can see that the average value of that is going to be a half. Yeah, make sense? Yeah. So what we have, of course, you could prove it, right? This slide just shows that you could actually prove it, but you have to apply, just like we did, take the Fourier series and apply the value for the calculation. Well, this is the trigonometric form, or you can, which is the form you have to use. If you use the exponential form of the Fourier series to try and prove this, you're going to land back up with the same issue that we started the class with, which is that you're going to land up with something like this, which can be evaluated. Okay, so you know how to do some of this already. The Fourier series of something, you would have learned this already, I think, in 2013. This was on the extra slides that I told you yesterday, how to find the Fourier series, the trigonometric form, if the period was not minus and plus pi. Okay, but you don't really need to know that. You could understand it straight from here, just by understanding what we did originally with the pulse. If I stretch the pulse out again, right, half the time it's 0, half the time it's 1, so the DC or average value is going to be a half. So that the answer that we're looking for is that the Fourier transform of the unit step is 1 over j omega, which is the part that we derive from the Laplace transform. And we have to add, there's a DC component to it, so we have to add the Fourier transform of a half. right? Because it has a half volt or half unit, whatever it is, in time. Yeah? So that is the complete answer there. The issue now is, what is the Fourier transform of a half? Right? So we do that by going into the derivative, the definitions that we have. A unit step, a unit impulse in time gives us a single one in frequency, right? So delta t gives you one in frequency. So if I were to put this in time, if I were to take now of an impulse in frequency, right? So I'm going the opposite here. Let me just backtrack here. So I'm asking a question. So delta t, let me just clear this a little bit. Delta t time frequency. Delta t in time gives me a 1 in frequency. What does delta omega in frequency give me back in time? Again, because we know there's some kind of symmetry going on in here. So chances are, at our first guess, I would say, okay, delta t in time gives me 1 in frequency. Delta omega, which is an impulse in frequency, probably going to give me 1 in time. Maybe, right? Think that's a good guess? It sounds reasonable. So let's see how reasonable that looks. If I give you delta omega in frequency and I ask you, well, what is the inverse Fourier transform of that? Well, you go back to the inverse Fourier transform, which is integral of x j omega e to the plus j omega t d omega. X of j omega is a delta omega, and of course we have this 1 over 2 pi that we spoke about, a little constant from yesterday. So if you put that in there, you're going to get that delta omega in frequency gives me 1 over 2 pi in time. We said 1, so we off by a little bit, but the idea is not too bad. So that an impulse in frequency, the inverse of an impulse in frequency is like a 1 over 6 in time. Just a place, a straight number, right? A constant in time. So therefore, you remember we wanted to find what is the Fourier transform of a half. Yeah? So this is telling me that the Fourier transform of 1 over 2 pi is delta omega. So a half is pi times this. Pi times this will give me a half. So that the transform in our, we're saying 1 over 2 pi gives me delta omega. So a half is going to give me simply pi delta omega. And that simply came out because of this little constant that we have in front here. Yeah? So in other words, the Fourier ft of a half is pi delta omega. So to complete it, an impulse in time gives me a 1 in frequency. An impulse in frequency, right, gives me a constant, in this case, a 1 over 2 pi in time. So in other words, a constant 1 over 2 pi for all time. If I take the Fourier transform of that, I'm going to get an impulse at omega 0. Kind of strange to figure out, but that's what happens when with the dual domains that we're dealing with here. So the complete answer, therefore, is that the Fourier transform of a unit step is 1 over j omega, right, plus an impulse at omega equal to 0. And what does that look like if you plot the magnitude? A very strange beast. So when you, again, sort of tying back to what we said about the unit impulse and the unit step being very powerful signals to put onto a system, when you put a unit step on a system in time, of course, you do certain things that we spoke about before, like you see the step response and you get the transient and overshoot and oscillations and all that kind of thing. But inside, part of the reason has to do with the incredible load. When you put the unit step, you put an impulse on the system as well, right? In frequency, you put an impulse at omega equal to 0. That's a DC, a sudden DC impulse that you give the system. And of course, you have some frequencies that start from very low and deteriorate as you go up here. So again, it's a very incredible test on the system. This impulse here also is part of the reason why the systems tend to oscillate if they're not controlled when you give them a step input, at least the higher order systems. Making sense? We'll go over it again, but I want you to think about what happened here, right? Not doing anything fancy. I'm just following what the definition of the Fourier transform is. Remember, we're going from time to frequency. Two different domains. Both of them we can see and measure, right? Unlike the S domain, you can't really do measurements in the S domain. But here, we can take a time signal, which is, in our case, where we just looked at a step, which is off and on. And what is that doing in frequency? If I were to look at the frequency components now, what it suddenly does onto me, it gives me an impulse at delta 0, right, at omega equal to 0. So there's a DC, a very strong DC signal coming in, which we expect because we did the unit step as an average value of a half. So there's a DC signal that is going to appear there in frequency, and then the magnitude of it decreases as a 1 over omega as you crank up the frequency. Right? So it's a sudden decrease, but it's a very sharp, as you can see in terms of the frequency that you put onto our system. It's a very narrow, sort of low frequency response that you impose on a system when you put a step response onto it. Yeah? Making some sense? Intuitively, at least. Right? I need you to understand, so the thing, right, and what I need you to understand is to go back here to this behavior, right? When we were talking about the dual in time and frequency, right? That what you know, that an impulse in time gives you, a constant 1 in frequency. What would an impulse in frequency give me? So intuitively, it should say, okay, it should give me a constant in time, therefore. And we just worked out exactly what that constant in time was, and it turned out to be 1 over 2 pi, right? So you have that behavior, that dual behavior coming in. And once you understand that, then the rest kind of falls into place. So that the Fourier transform of the unit step is 1 over j omega, so the magnitude of that will be 1 over omega. And there's a DC component, and we see that because we saw that the thing is off for half the time and on for half the time, so that there's some other component going inside of here. And again, if you remember everything that we've spoken about before too, when we looked at some of the changes in signals, every time you do this, that, see that sudden change? Every time you impose a sudden change on the input to a system, you're going to create an impulse somewhere, either in frequency, or if this thing goes through a derivative, right, you're going to get an impulse being created. All right, so steps, that is why discontinuous, and we made that point. If you have signals coming in suddenly discontinued, and then it starts back again, suddenly discontinued, and starts back again. These sudden changes all act as steps, which all translates into impulses, which all stress out the system, right? Systems, if you don't design systems properly, and this will come up later on, and maybe in your professional life, depending on where you land up. If you don't design systems to cater for interruptions and handle them gracefully, then you're going to run into problems, because you could see what sudden changes cause. Yeah. And just to close, here's a little one, and this one you just think about it in terms of the property. What is the Fourier transform of a cosine signal? And the hint there is, remember what was the spectrum of that? How we drew the spectrum of that signal. This is where we started all of this thing. So what would be the Fourier transform, also known as the spectrum of a single cosine pulse looking like that? What would a cosine pulse spectrum look like? You have that. Some of the properties that we looked at in the previous slide already of the Fourier transform. And what we started the very first couple of slides when we spoke about going from time to frequency, and how it looks in time and how it looks in frequency. And you should be able to figure out what the spectrum of something looking like that would be. In other words, if I apply the Fourier transform to that, what would my answer look like? So questions? Yeah? No, maybe? All right, still recovering. Still recovering. Yeah, of course, they're still recovering. That's why I kept the class to 1 hour today. So, okay, so let me just stop the recording here for the time